Yunguo from USDC speaking with us. And Yunguo actually got his undergraduate master and PhD in material science, first at Shandong University and then in Sweden Institute of Technology. But afterwards, he moved to earth sciences, working at UCL, and he worked on the various topics that our earth scientists are quite interested about, such as hydrogen, noble gases, magnesium in the Earth's core. And so today he's going to talk about that hydrogen story. So with that, I'll give the rest time to Yunguo.
Thanks for introduction. And welcome to my talk. So today I'm going to talk about the water in the Earth's core. Normally, not so many people care about the core because it is far and deep in the Earth. But with the advances of new hyper techniques and our understanding of the Earth, the core becomes more and more interesting. So for those people who are not familiar with the core, let me give you a short brief introduction of why we studied the core. So the core forms very early. So well before the end of the growth of the Earth. So after formation, it is pretty isolated from other geodynamic processes. So it must have recorded many early Earth informations, and also the interactions, the chemical heat exchange between the core and mantle still plays a very important role in the interior dynamics. And most importantly, the geodynamo and geomagnetism that generated in the core is fundamentally extremely important to all creatures, including Earth on the Earth. So to decode so many useful informations, we need to know the structure and the compositions of the core matter, and also its physical and chemical properties. We have several techniques that allow us to use. From seismology, we can know the internal structure and the pressure, density, and velocity profiles about the core. We know there's an outer core and inner core. And the geochemistry and cosmochemistry can constrain the identity and concentrations of light elements in the core. So the core is mainly formed by iron, and with less than 10% light elements, there are less light elements in the inner core. So silicon, sulfur, carbon, oxygen, and hydrogen are the most promising light element candidates in the core. So within this multi-component system, there are many accommodations or solutions that can satisfy the outer core properties because it is liquid. So outer core itself doesn't act as one strong constraint for the core study. And on the contrary, for the inner core, the solid core, we didn't find any exact solution so far. So for that, we need to resort to high pressure, high temperature experiments or simulations. So the pure ion density and velocities are much higher than the prior model. And for the other compounds like iron silicide, iron carbide, all these compounds have higher some velocities than the prior model at the inner core density, and some compounds even much higher have even much higher velocities than the pure ion. So far, there's no solution for the inner core. And the most recent iron 7 carbon 3, it is expected to match the prior model some velocities, but the density is found too low. we haven't found one exact solution for the inner core. So, but we have almost exhausted the possible compounds. So the problem is that we might have been on the wrong path. Okay. So now the core composition could be on the hypoeutectic region and not on the hypereutectic region. In the hypereutectic region, we have the compounds precipitate as the core candidate, but in the hypoeutectic region, we only have the ion solid solution. For the possible light elements, oxygen, hydrogen, silicon, sulfur, and carbon, they all have very high eutectic compositions. For oxygen, it is over 10%, and for hydrogen, it's also about 50 mole fraction. For sulfur and carbon, the eutectic point composition is above 3%. With this high eutectic compositions, so the density of the compounds would be much lower than the present model. Silicon has the lowest eutectic composition among the 5 light elements. But even so, the iron silicide also has a lower density than the present model. And besides, its sound velocities are much higher than present model. So it's unlikely that the current composition will be in the hypereutectic region. So we think that it should be in the hypereutectic region. And we explore this multi-component system, and we calculate the thermoelastic properties in the iron, silicon, sulfur, carbon quaternary system. And we found many solutions that can match the inner core density, sound velocity, and Poisson ratio simultaneously. But all these solutions must contain carbon. The problem is that carbon, unfortunately, it doesn't partition into the solid ion. So it's very incompatible. So that's an awkward situation. We have only 2 other options left: the oxygen and hydrogen. Oxygen behaves similar to carbon. It doesn't partition into the solid ion. So hydrogen is our only hope. The question is, can hydrogen partition into the core? And is there significant amount of hydrogen present during the core formation? Our Earth is water rich, but it formed in the relatively dry region, and the water on the Earth could come from the building blocks, the chondrites, or it can be from the nebular in-gassing or comets. But for the source of water on the Earth, it is heavily debated. Initially, it thought that the building blocks like ancestite is very dry and cannot bring water to the Earth. But recently, that it seems that ancestite may have enough water that can contribute to several oceans water to the Earth. And besides that, nebular in-gassing is also one possible source for water in the Earth. The terrestrial planets like the Mars formed very early in the solar system, well before the end of nebular gas dissipation. So nebular gas in-gassing is also very likely. So ocean and sharpest study modeled the ingassing process. They found that over several tens of oceans could be brought by nebula ingassing to the Earth. So during the core formation, the Earth could have gained much water. The question is then can water partition into the core? Early in 1996, Chromoto calculated the partition of water between liquid iron and silicon melt. He found that water is siderophile. And almost at the same time, Okuchi did the experiment at like about 7 GPa. He found that over 95% water enters the liquid ion. And also in 2012, that in my experiment, for water partition between the liquid ion and rainwooded, so water is also shown to be siderophile. So if this story holds that we can have a lot of water in the Earth's core, however, the following studies, the most recent studies, show that the story may be very complex. And this classic result, he found that at low pressures, the water may be lisophile, and it is dependent on the pressure. And Malavagni's results show that it is also dependent on the oxygen viscosity. So this study show that the water partitioning is heavily dependent on pressure and oxygen viscosity. But with these information, especially at low pressures, we cannot predict how much water will be in the core from this data. So we need to get more complete and data at high pressures. So we did free energy calculations to derive the partition coefficients of water between liquid ion and silicate melt. So the partition is some dynamic problem. We need the chemical potentials, and that is derived from Gibbs free energy. And for this, some dynamic terms, and they're all determined by the forces, that how atoms will interact with each other. To describe this, we need a force field. There are many empirical potentials we can use, but the disadvantages is that it needs to know how the system behave before we do simulations. It is not possible for us to, when we study high pressure things, especially the core, because we don't know how. That is what we want to know. And there are other disadvantages for the empirical potential, because it lacks transferability and it have a poor universality. So with regard to the quantum mechanics, because the interaction between atoms is actually a result of the electron interaction that is described by the quantum mechanics. And the quantum mechanics, the heart is the Schrödinger equation, H phi equals E phi. Phi is the wave functions of electrons, and H is the Hamiltonian, and E is the total energy. The total energy contains the kinetic energy part and the potential energy part. So also the Hamiltonian contains these two parts. The Schrödinger equation can be solved analytically for single electron system, but for many body systems, it is hard to we don't know the exact form for the Hamiltonian, because we don't know how the form of electron interactions look like. So we have to resort to approximations that solve the Schrödinger equation numerically. So one of these methods is the Hartree-Fock method. And Hartree-Fock method uses this single-slater determinant wave functions. When we put this function into the Schrödinger equation, we get the expression of total energy as like this. So the last two terms is the electrostatic interaction and the exchange energy. Now, this term is the kinetic energy for the single electron, and this term is the electron nuclei interactions, electrostatic interactions. So it assumes that the electron moves in a mean field of formed by the nuclei and other electrons. So if we simplify this kinetic energy part to single electron kinetic energy part energy term. So it neglects the instant interaction between the electrons and electrons. So the Hartree-Fock doesn't consider the correlation between electrons. So it's we call this the correlation energy. And this energy is about 2% of the total energy. It's small, but it is equivalent to the amount of chemical reaction energies. So it is very awkward. Some post Hartree-Fock method were developed to account for the correlation, but the disadvantage of Hartree-Fock method is that it uses the wave functions. It is a wave function method, and it's later determinant. Okay. Now here you have so many wave functions. For each wave function, that it contains at least 5 variables. So with so many variables, it's hard to solve. So far, the Hartree-Fock method can only be applied to very small systems like molecules. The other one choice for solving the Schrödinger equation density functional theory is based on the HK theorem. So it states that the external potential and total energy of the system is uniquely defined by the electron density. So the influence of this theorem is that it considerably reduces the amount of variables used for solving the Schrödinger equation. Before that, we have so many variables, and now you have only 3 variables, x, y, z, to describe the density. And the second, the theorem says that there is a functional that produces the minimal total energy when the electron density is in the ground state. So, on this theorem, we can rewrite this equation to Constraint equation that it's the total energy is expressed like the kinetic energy of single electron and electron nuclei interaction energy, electron and electron electrostatic interaction, and the last term contains all the terms we don't know. So it contains the exchange and correlation interactions. If this last term is exact, if we know this term, then the total energy will be exact. So this simplifies the solvation of the Schrödinger equation, and but we don't know the exact form of the exchange correlation function. This term contributes about 5%, less than 5% of total energy. So it is very important because we most time we care only about the chemical reactions. if we use the exchange correlation term of uniform electron gas, we can get the local density approximation for the exchange correlation functional. The uniform electron gas, the exchange correlation interaction can be calculated exactly from Monte Carlo simulations. It is only one system that we can know exactly, because the electron density is not uniform everywhere in the real materials. To account for that, we might we can add the corrections to the local density approximation, like we can add gradient terms and also higher order gradient terms into the exchange correlation function. In this way, we get a series of other approximation for exchange correlation interactions, like the GGA and the meter GGA. We can also bring in the Hartree-Fock exchange term into the exchange correlation functional. Then we have the hybrid functional. So this, from LDA to GGA into hybrid functional, the exchange correlation functional becomes more and more complex, and the calculations also becomes very expensive, but the accuracy will be improved gradually. So this forms a Jacob's ladder. So in the heaven, in the end of the ladder, it is the exact exchange correlation functional. The closer we are to the heaven, the more accurate our result will be. But we don't know whether this heaven is really whether the heaven does really exist. So let's see the accuracy for the basic functionals. For the ionization energy and affinity energies, that LD, GGA normally are very good. The deviation from the experimental results is normally below 2%, and GGA normally is better than LDA. For the bond length, atomization energy, and volumes, these terms meet LD and GGA are also very quite satisfactory. The difference with the experimental results is normally with 2%. So this is for exact result. But if we want to study the trending, the physical trending or chemical trending for the chemical reactions or influences of some factors, the system errors will be cancelled. So we might have more accurate results for the physical and chemical trending properties. So we use the density functional theory to calculate the free energies for our liquid ion and solid silicon melts. And the free energy is an integral in the phase space. It is not a simple sum average, so we cannot calculate directly, and because the convergence is very slow. But if we have one reference that with the known free energies, we can convert the calculation of free energy to calculate at the sum average of the potential energy difference. So that is why we use some dynamic integration to calculate the free energies based on the molecular dynamics to get the averaged potential difference. This figure shows the calculated partition coefficients between liquid ion and silicon melt. So we have considered two cases. One is pure hydrogen, and the other one is pure water to represent the reducing and oxidizing conditions. The square one, a square symbol, represents the result for the pure hydrogen, and the circle represents the results for pure water. From the small to big symbols, it represents the results for composition from 0.0% to 20% of hydrogen, 10% in liquid ion. You see, for hydrogen, it is always hydrophile above 1 from 20 to the command boundary conditions. And for the water, it is hydrophile at high pressures, but there's a sharp increase from 20 to 50. And this trending seems to be consistent with the finding by Clasey and Magni. They found here this pressure dependence. So we think the difference between a discrepancy between experiments may origin from the difference in oxygen fugacity. And actually, in Okuchi's experiments, it is like pure hydrogen, and in Clasey's results just like to be water. So why there's a sharp increase from 20 to 50 GPa? So we can look at the chemical potentials of water. As water chemical potentials plotted, the red one is for silicon melt, the black one's for liquid ion. You see, for the silicate melt, there's a sharp increase from 10 to 50, and then it is more slowly, more smooth after 50. So why is that? We think so we can look at the silicate melt structure. From 0 to 50 GPa, there's a very fierce change of local structures. The coordination numbers become is considerably increased. For this one, it's like a silicon oxygen. The coordination for silicon with oxygen is increased significantly, and also for magnesium. And this one shows the oxygen of the coordination between oxygen and oxygen. So it increases significantly from the low, from 0 to 50 GPa. So when the coordination number increases, so the repulsion between oxygen anions will be stronger. So that will increase the chemical potentials of oxygen. That's why there's a sharp increase from 20 to 50 GPa for the chemical potential of water. In the liquid ion, the chemical potential first increases smoothly, and then it increases sharply. It is the opposite to what is happened in the silicon melt. This is because that oxygen has a very small volume at low pressures, because it's small. And the liquid ion has a close-packed structure, so oxygen atom doesn't subject to very effective compression. Only at high pressures that it changes from the interstitial conditions to the like a pseudo substitutional sides, then it can act like iron atoms, and the compression will be more effective on oxygen atoms. So this changes of chemical potential can explain why we see the sharp increase of water partition coefficient from 20 to 50 GPa. We also calculate the temperature effect on the partitioning. We found with the increase of temperature, the xerophile behavior becomes weaker and becomes approaching the neutral behavior at high temperatures. We think this is close to our expectation, because at high pressure and high temperatures, the silicate and the liquid ion melts. They are close to the ideal cases, and with the increase of pressure of temperature, the structure will become more ideal. So for ideal gases like ideal liquids, that the solution will be neutral. Besides that, we also use two-phase modeling to empirically count the numbers and to derive the partition coefficients. So we set up a soup cell. This is the soup cell. So in left side, this is the liquid ion region, and in the right side, this is the silicon melt region. And there are two interfaces. At the interfaces, we inserted 12 hydrogen atoms, 6 at each. Then we start to relax the structures, and at the end, we collect the trajectories of hydrogen atoms. You see the hydrogen atoms most time reside on the liquid ion region. So this confirms the xerophile behavior of hydrogen. But this simulation only lasts for like 10 picoseconds. It is not converged. This only shows the xerophile behavior of hydrogen, but it cannot give the accurate partition coefficients. To use this method to get converged partition coefficients, we need to run the MD over 150 picoseconds. So this is one converged partition coefficients. And we count the numbers of hydrogen in the liquid ion. So this blue curve indicates the number of hydrogen atoms in the liquid region. You see it fluctuates strongly at the beginning, and with the increasing of modeling time, the fluctuation becomes the normal and approaching the convergence. Here's the orange curve is the calculated partition coefficients from the trajectories passed. So the converged partition coefficients are matching our free energy calculated results. We have another method to calculate the partition coefficients from the two-phase modeling. So when it is converged, we can see that we can plot the density distribution of elements along the z-axis. So this x-axis, this horizontal curve. Oh, no, that's not curve. This is horizontal axis shows the represents the z-axis in this soup cell from 0 to 1, and the y-axis shows the density of these elements along the z-axis. When this converge, when these simulations converge, you can see the at the middle of the liquid ion or silicon metal region, the density is it's flat. So we can fit the height for these two flat region for hydrogen, and use this flat concentration, flat region concentration to derive the partition coefficients. Now, the derived partition coefficients also match. It's the same to the one we calculated by counting the number of the hydrogen in liquid ion. This is the short video about this two-phase simulation. I will play this video to show you how the atoms behave in the two regions. You see, the white ball is the hydrogen atoms. It moves quickly into the liquid ion region. Some may enter the liquid silicate region. And in silicate region, it's bound with oxygen from hydroxyl. And in liquid ion, hydrogen moves freely like free atoms. Okay, I cannot. Okay. So with our calculated partition coefficients, we anticipate that the core may contain about five oceans of water. If we assume that there's only one ocean of water left when after the left in the mantle after the core differentiation, and this is consistent with the estimate given by Wu, who estimates this number by studying the hydrogen isotope fractionation during the core and the mantle. And Hollis also Hollis plotted when the water concentration against the hydrogen isotope deviation, and this is the MOB, and this is the from ocean island basalts. These materials are thought to represent the deep mantle materials. So the highest water concentration is about 0.2%. If the deep mantle has so much water, the core would have over 15 oceans of water. So it's much higher than our estimates. So we think this ocean island basalt may have been contaminated during its ascending process, because there are many water in the regions like transition zone, mantle transition zone. So we have water and hydrogen in the core. So how that will contribute to the core, to the inner core properties? So Yunguo Wang recently calculated the thermoelastic properties of iron hydrogen alloy and iron silicon hydrogen alloys. I found that the binary and ternary can both explain well the inner core properties. So we are now very close to have an exact solution for the inner core. To summarize my talk, so we predict the water will enter the core, and because water is highly stereophile, so so the deep mantle anomalies, including the LL, SVP, and the ULV zone, VZ zone, should be dry. And the subducted slabs, if it can reach the chromatin boundaries, though the water will also enter the core. And it's not possible to form compounds because the core is in the hypoeutectic region. All this will mean a constant change of the core compositions. So that's all for my talk this time. So this work is done in collaboration with Lidinka, John, and Tom. So in my talk, I also include some results from collaborations with Ian, Wenzhong, and Mata. Okay, my talk finished here. Thanks.
Okay, thank you very much. Now it's time for questions from our participants. So feel free to open your mic or leave questions in the chat, and I could read it for questions. Okay, I would ask a short question that as in your last slide that the course compositions constantly change. So from your perspective that this evolution of the Earth's core, so how does this evolution of Earth's core composition impact Earth's mantle composition? I would think of, let's say, it's a mass balance in the long run, but I don't know that what's the mechanism that, for example, if the core that loses interact hydrogen with the mantle or the other elements, you may have or have not talked about this topic, like magnesium or noble gases. So what is your perspective? How does this core mantle interaction occurs, infer from the constant change of core composition in the Earth's history?
So I mean, here's about the water in the core. You talk about the magnesium and like silicon. So of course there are changes for these elements like magnesium and silicon. But here I mean that water in the core is changing because we have subductions and it delivers water into the core. But for the silicon and magnesium, that we know the core is cooling down, so the solid solubility is decreasing. So that is so we have a more silicon oxide, like silicon oxide and magnesium oxide precipitate in the future from the core. But for the water, it is largely under the composition of the solubility. So water will be more in the core and not less.
Okay, hello. Yeah,
Hi.
it's a very interesting talk. So I may ask a technical question here. So
Okay.
in your thermodynamic integration, so do you have the endpoint problem because you integrate from 0 to 1? So sometimes that the energy at 0 and 1 maybe it's difficult to convert. So do you have that problem, or how you choose your reference state here?
Yeah, if it depends how different is your reference system to your system. If they are close, so the transition, the path will be smooth, and your travel, your journey will be easy. But if they differ significantly, yeah, you may have that problem that it's the path is very curvy or it's sharpy. It's sharp, so you need many points to convert the results.
Okay, and also here in the thermodynamic integration, so did you include the two ends? I mean, lambda equals 0 and lambda equal 1. Did you include both of them, or extrapolate them?
We have that too, because the one, like a 0, at the one end it is your real system. At the end it is the known system. That is already known.
Okay. Okay, thank you.
Welcome.
Okay, if we don't have more questions, then our seminar will end now. And thank you again, Yunguo, for giving the talk, and thanks everybody for the participation today. Okay, have a good day.
Thank you. Bye-bye.